Right, so I think I have some of the 5.1 stuff, so I'm going to go over how to do that. All right, so I'll start with stuff that's done already. Mainly this table down here. So everything's filled in. So where are these things coming from? All right, first off, we got the time. Okay, you notice these go up by intervals. So we have every 50 seconds. Okay, you always see that it'll always be like the going up the same amount. And then we have this, which is coming from some measurement somehow. A few different ways to do the measurements. So they're saying that look at like mass lost, molarity from the spectrophotometer, things like that. Um, so how do we get from these ones to these ones? So this is a bit of stoichiometry here. What you want to look at is how one changed to the next one. So this one went down 4, this goes down 2, and this goes down 1. And we're going to set a basic fraction here. So we have this HNO3 that is this, and it is being reacted with copper to get this. So for every 8 of these, you have 3 of these. So that's where we take these numbers. So as a sample calculation, I'll use, I forget what colors work out here best, but we have 4 of these minus 4, but I'm going to take the signs out for a second. Okay, so that's 4 of the H's. So for every 8, we get 3 of these. That is 12 over 8, which is 1.5. So at 0 time, you don't have any of the products. Um, you just have these reactants here. So that's why there's initially a 0. Then it goes up by 1.5. And so I'm going to clear some of this out to make this clearer. So I'm going to use this number. This is going up 1.5. So 0 plus that is 1.5. Now I'm going to do the calculation again, but this time with that minus 2. So I'm going to say 2. When you're doing these calculations, you write out everything. You write out like the HNO3 and so forth. Just trying to save a little space. So for 2 of the HNO3s, you have 8 HNO3 on the bottom, 3 on top. That's just from this right here. That is 6 over 8, which is 0.75. Now notice that's not this number here. We get that by adding 0.75 to the previous number. All right, so it's this addition. So I'm going to add 0.75 here and do the same calculation with this -1. So you have 1 HNO3 multiplied by the same fraction, 3/8. So that's 3 of the copper, this guy here, and for every 8 of those. So that's 3/8, that's 0.375. So I'm going to add that on to this one. So every answer depends on the one before it. Next column, we're going to figure out the rate for all these, how it changes. And the rate changes is not constant. We don't fill these out because we're just starting. So we're going to see what happens from this one to this one. So it's starting at 8 and going to 4. So it's going down. That's why we do subtract in this order here. 4 minus 8, we get -4. And then it's over the time difference. So 50 minus 0. The time difference is always going to be 50 for these because of the way it's going up here. and then we just get a decimal value for that. Okay, again here, we're going from, see what happens to get to here. So we do 2 minus the 4 over 100 minus 50. It's pretty much like y2 minus y1 over x2 minus x1, which is this formula here. So it's like doing change in y over change in x, like slope. The only thing is the slope is changing from point to point. Right, so then the last one we would do 1 minus 2 over 150 minus 100. That is this calculation right here. And then we get this value. The next column you do the exact same way. So for this, you're going to do the same thing, but use these numbers. Yeah, that makes sense. Okay. And then the same time differential will be 50 seconds. And on to the last column. Where does all this come from? Okay, so the X again is because we're just starting, so there's no right there. This is a little unclear the way they put this. The reaction rate is found by dividing the rate by the coefficient to get a value when the coefficient is 1. That's the confusing part there. I would say what you could do is you could take either this column or this column and the rates given and divide by the coefficient from the equation. So if you take this value here and divide by 8, because of this 8, you'll get this number. And then you could take this one and divide by 8 as well. All these would be divided by 8 because they're all about the HNO3. And you'll get the numbers in the last column. The other way to do this, and you'll get the same answers, is if you took this column here and divided everything by 3. Okay, the 3 is coming from the 3 copper, I'm gonna mess up the names of these things, copper nitride, I guess. Divide all these by 3, and you'll get the same thing in the last row. All right, so with that said, let's go on to problems that aren't done already. Okay, share that one. All right, just really quickly, what's going on with this? They want to know at the top what conditions will cause their action to go the slowest. So I do I'm gonna do an analogy here. So you have small chips and powdered. Small chips are kind of like a hard candy. So like butterscotch or where this stuff nobody eats unless you're like over 50 years old or something. So those take a while to eat. They're like a lollipop, you think. Small chips are like lollipops. They take a while. Okay, so for the slowest, that's where the small chips belong. Powdered, very fast. Powdered is like a pixie stick. Those are these like paper things filled with sugar. You just eat them. It's quick. That's powdered. That's fast. Other conditions here. We're looking at the hydrochloric acid. If it's strong, it's going to make it go faster. Because it's kind of like you could think of it like acid eating through something. If there's stronger acid, higher molarity, it's going to go faster. That's why this is here. Weaker, it's going to go slower. And the last thing, if something is warmer, the reaction will go faster because higher temperature means that molecules or atoms are moving around faster. That's what temperature means. It's based on the energy, the kinetic energy of the molecules. So warm water bath will be faster than the ice bath. All right, what do we do here? Rate of disappearance is okay. They're giving you the rate of disappearance, and they want to know the rate of appearance. Some pretty simple equations. So one's changing into the other. So what we do here is basic stoichiometry. So you start with this rate. You don't have to worry about the sign because disappearance is negative, but we're gonna have positive here because we're creating something. Okay. So is this, and I'm gonna put in that this is about the ozone. So this is about the O3. So you have two of the O3s for every three of the O2s. So you're taking this rate and multiplying it by 3/2. I got the work for this. So I'm just look up the number quick. Okay, this is going to be 0.0051 meters per, not meters, sorry, it's molarity per second. That's positive because it's forming. So that should be the final answer there. Now for the rate of the reaction, that's also always expressed as a positive. So there's two things you could do for the rate of the reaction. Just like the previous page, you could do something with the products, or you could do, sorry, reactants and something with the products. I think I'm like mixing up those words sometimes. Um, so the reactants are on the left, products on the right. So yeah, previous videos I messed those words up, but I think you get what I mean. So rate of the reaction, you would do either this, which is about the ozone, excuse me, and you could divide that by the two because of the coefficient with the ozone here, and you'll get an answer that way. Or you could do this guy here. That is the products. Okay, so you got this divided by, okay, so that's about the formation of oxygen gas right here. The coefficient is 3. Okay, so either way you get this value. So you get 0.0017. That is molarity per second. And as I said before, a rate of reaction should always be expressed as a positive, regardless of what you're using to find it. That's my iced coffee. That's what you heard, ice clinking. Um, what's all this? Okay, so in the you do here, this is done like the previous page. You want to consider what happens from one step to the next. So we're doing this kind of thing. Now, these values are given to us. We need to go off of something, right? And those are going to help us find what these are. So I'm not sure where these numbers are coming from, but I'll show you how it's done here. So we're going to look at what happens from step to step. So the first thing I'm going to do is fill in some of these numbers. Now, these are all going up 100 for the time. I don't think we need that here. We just need to know what's happening here. So these are all minus. So you're losing 0.05 to get from point, it's like 0.20 down to 0.15. It's 0.05. Then you're losing another 3/100ths here. So that's going to be minus 3/100ths like that. No, I didn't see that 5 there. 3/100ths. It's this. I'm just finding these by subtraction. I just have the answers from before to make it quicker. 0.0125. You see each time it's losing a little less, so the reaction slows down over time. Okay, so what I'm going to do with all those is going to just going to draw on this for a moment. So we have this. This is saying how much you lose of the N2O4. Now for every one that's lost, you're gaining NO2s. NO2 on top and 2O4 on bottom to make those cancel out. That's all molarities. And then we look at the equation here. We have a coefficient of 1 and 2. So the 1 belongs here, 2 on top. And calculate, we get 0.1, leaving as a positive because something's being formed. So this is 0.1 of the NO2. We're going to do that same calculation for everything. Now, to simplify things a little bit, I'm not going to write all the letters here for the chemicals. So next, we're losing this much, and then times 2 over 1. So 1 or 2, and that gives us 0.15. And the last two numbers we got is guy times 2 over 1, so times 2. 75, and then that times 2. I'm looking right now and I realized that I did mess up something in the initial, believe. Let's see. Back up a little bit. I'm copying down the wrong numbers here. Okay, so ignore these guys. That's what not what wasn't making sense here. Okay, so 0.25 0.25 times 2. This is it's gonna give you this. So just completely ignore the numbers I just said before. 0.025. And then I'll explain why I wrote those. So you notice that these numbers are getting smaller each time that this the formation, the reaction slows down. So these numbers do not belong up here, except for the first one. So we start off with nothing, and then we add this much. So you're going to add 0.1 of this, and then you're going to add this to that. Okay, so we're going to take 0.1 and add 0.05. We'll get this. Now I'm going to take that 0.15 and add this much. Then I'm going to take this 0.175 and add this much. Okay, so this problem is done. Just to clarify what we got all this here, we do 0 plus 0.1, then 0.1 plus this guy to get this, 0.175 plus this guy to get this, and then this to this, you add that. So these here are the changes and everything, and much like these are the changes here. So we use the changes in the N2O4 to find the changes in the NO2, and then we add them. So they're subtracted over here because it's disappearing, and they're added here because they're appearing. All right, so now to get rid of that so you could see the answers more clearly here. I'm gonna get rid of this work here because we're gonna fill in this graph next. So the first part looks like you did, looks good. All right, so you took those from all these numbers that's disappearing right there. And it wants us to do for the NO2. So we start up with nothing, that's down here. And then we go to 0.1. Then to this 0.15 here. 175, that should be in the middle here. And then this one, this value here, a little bit below the 2. I'm not very good at drawing these lines in the computer. Still at best here. And it's going to be a curve like this down to here. Forget that dot. All right, so I'm going to end this video here and do another one if there's another page.